Good morning, friends. It's give me immense pleasure to be here again for my class, Flight Mechanics. I am in the pursuation of this course, and I am in module 4, which is turning flight. Today, my topic is turning rate and spanwise velocity. So we will see that. Yes, I am Dr. Yagya Dutta Dwivedhi, professor from IARE Hyderabad. In today's topic, I am going to discuss about turning radius, turning rate, maximum load factor during spanwise flow, maximum velocity, minimum radius. These are the topics for my today's lecture. So first I will discuss about turning radius, and here I have the three views. First one is the front view. This is the front view here. This is the side view, and this is the top view of the aircraft when it is flying in this way. So I will start with the side view here. This is the aircraft. It is moving with the velocity v, which has got gamma as a flight path angle. Velocity is v, which is inclined to gamma from the horizontal. And we are also assuming that the thrust is also in the same direction as the velocity. If you see here, the weight component, and this is also gamma. So the component which is opposite to this lift component, L cos phi, is W cos gamma. And if you put a camera here, this is the camera. In this camera, if you see, this weight will be observed here in this front view as a W cos gamma, not the W. And also this L cos phi will be here. This is the L cos phi, this one, and this one is L sin phi, and this is the L. Your aircraft is banked by phi from the horizontal, and if we see on the top view here, it is turning in this direction with the radius r. This velocity v will be experienced from the top. If you see in the horizontal, this will be v cos gamma. So this is moving with the v cos gamma. Here is a L sin phi. This L sin phi is visible from here. So this L sin phi will be countered by the centrifugal force, which is W by G V cos gamma whole square divided by R, VR square, MV square by R. Here V is a V cos gamma. So the velocity which is tangent to this aircraft is V cos gamma. Now we will see that here L sin phi, in this figure number 3 I am writing here, figure number 2 and figure number 1. So from the figure number 3, if we see the force balances, equations of motion, we will see that L sin phi, this here. So here this L sin phi is equal to W by G V cos gamma whole square by R here, and L cos phi, this is the from second diagram here, L cos phi is equal to W cos gamma. So if we square it, this L square sin square phi plus cos square phi is equal to W by G V cos gamma whole square by R whole square plus W square cos square gamma. So this sin square phi plus cos square phi is equal to 1. So here we will have L square is equal to W square by G square R square V square cos square gamma whole square plus W square cos square gamma. So from here we have to find out this R. R is turning radius. R is turning radius. So we have to see that. So here we can see that L square minus W square cos square gamma is equal to W square by G square R square V square cos square gamma whole square. So from here if we take the R square here, so here W square by G square V square cos square gamma whole square divided by L square minus W square cos square gamma. So here R is equal to here W by G V square cos square gamma divided by under root L square minus W square cos square gamma. We can further simplify and we can write that V square cos square gamma divided by G, we have taken this W square, the below under root, so here L square minus W square minus cos square gamma. So L square by W square is equal to N, so it is N square. So this R is equal to V square divided by G N square minus 1. Because we have taken this thing out, so here this is the equation for turning radius. So we got the first equation for the turning radius, that R is equal to V square by G under root N square minus 1. Now we will see the next turning rate. So turning rate is the angular velocity of turn and it is represented by omega. Recalling, angular velocity is just translational velocity by radians, that is Vt by R. So this omega is equal to Vt by R, and here for Vt we can write V into cos omega by R, where omega is a very small, so we can write that cos omega is equal to 1. So omega is equal to V by R. R we have just got from the previous equation number 1, that is R is equal to V square by G N square minus 1. So angular rate omega is equal to V by R, and so here we can write that G under root N square minus 1 by V. So we, for the stall limit load factor, that is N maximum, it should be half rho V square divided by W by SW CL maximum. So maximum turning rate, putting this equation in the equation number 2 here. So now omega maximum is turning rate maximum is equal to G rho V square by 2W SW CL maximum V square minus 1 by V square. So turning rate by structural load limit 2 for the positive N maximum. So this for the positive N maximum, and load factor maximum is equal to load factor for positive load limit W maximum by W, putting in equation number 2. So we will get that turning rate, maximum turning rate omega maximum is equal to G by V under root NPLL W max by W whole square minus 1. This is the maximum turning rate at maneuvering point when velocity is Vm, that is the point 1. So this is the point 1 which is represented here, And so this velocity at the point 1 Vm is equal to under root 2 NPLL divided by CL maximum under root W by SW by rho. So this is the maximum velocity at the maneuvering point. So if you want to find out what is the velocity at the maneuvering point, so you have to use this equation, that 2 NPLL, where NPLL is a load factor, positive load factor limit, divided by CL maximum. So here is the positive, this is the NPLL. This point is the NPLL, positive, and this is the negative load factor. It is a positive load factor, it is a negative load factor. So W by SW divided by rho. So putting this in the omega maximum equation, we can get that maximum turning rate is equal to under root CL maximum by 2 NPLL W max by W minus W by NPLL W max G under root rho by W by SW. So this is the maximum turning rate at maneuvering point 1. So this we have got it. Now we will discuss about steady coordinated turn span-wise velocity. So as of now we have seen the radius of the turning. The turning radius is V square by under root G V square by G under root N square minus 1. And then we have seen the turning rate, and this turning rate we got the maneuvering velocity Vm, and this maneuvering velocity depend upon the load factor and the CL maximum, weight and the wing loading, also the altitude of the aircraft. Then we have find out the maximum turning rate. This maximum turning rate is equal to under root CL max by 2 NPLL W max by W minus W by NPLL W max G under root rho by W by S by W. This is the maximum rate of maneuvering point. Now we will see that what is happening when the aircraft is turning coordinated turn with span-wise velocity. So we can see that if this is the aircraft which is shown here, this is the aircraft, here is the center of gravity, this is the inner wing, this is the outer wing, and it is turning like this. It is, if you see here, okay, this is the aircraft and it is turning like this. So turning radius is here, this is the inner wing and this is the outer wing. So there is a difference of the velocity in the inner wing than the difference of the velocity at the outer wing. This inner wing and outer wing, if we see the span of this wing from this tip to this tip, this is your span, and if you take the half, it is a b by 2, it is called the semi-span of the wing. So the velocity on the inner wing is different than the velocity on the outer wing. So how much it will affect the aircraft performance, how much it will affect its other parameters, that we are going to discuss in this class. So as of now we didn't consider span-wise velocity. What happens if we consider span-wise flow and velocity? Differences in velocity seen by different parts of the wing span, much higher velocity at the outboard than the inboard. So if you see, this is the outboard, in this velocity is high and in this velocity is low. So here it is shown by the arrowhead, it is high, and here it is, comparing to this, it is less. So we assume that variation of the velocity is linear. So if we see here, the velocity variation is linear like this. So this and this. So it is a linear we are considering here. So we know that v is a function of the radius. So here it is a small radius is from the center to the inner one, it is a small one, and from here to here it is a capital one. Means from center to the outer tip is capital R and the inner tip is a small r. So v is a function of r is equal to vcg, means if the velocity is here vcg small r by capital R, where small r is a small radius and capital R is a radius from the outer wing. So R inner is equal to, we can write it R capital minus b by 2 cos phi, where phi is a bank angle. So R inner we can outer we can write as a R plus b by 2 cos phi. So now the velocity of inner v inner will be v of cg into R minus b by 2 cos phi divided by R. So vcg here 1 minus b by 2 R cos phi. Okay, so here we are small r and this is the capital R. So this small r here it is given R minus b by 2 cos phi. This we have put here. So after putting this, if you see that this cancel, we got here 1 minus b by 2 R cos phi. So same way for the velocity, this is the inner wing velocity and this is the outer wing velocity. So inner wing velocity and the outer wing v outer is equal to vcg 1 plus b by 2r cos phi. So we got this two velocity and we can understand that one is a plus from the cg, another is the minus from the cg. The inner wing will have less velocity and how much less? It is b by 2r cos phi. And outer wing will have the additional velocity which is 1 plus b by 2r cos phi. Now we have to see the maximum load factor during a spanwise flow. We have seen that CL is equal to half L by half rho V square SW, where V is the velocity, rho is the density, SW is a wing area. If velocity V is low at inner point, so CL will be high. So if this velocity is low and in inner, so CL will be high. Recalling load factor maximum, that is N maximum, is given by the equation N maximum is equal to half rho V square inner divided by W by SW CL maximum. We can write it as half rho V square CG 1 minus B by 2R cos phi maximum into CL maximum. So here we can see that we have to figure out that load factor maximum is equal to 1 by cos phi and R is equal to V square by G under root N square minus 1. Now we can write this equation 1 above by putting these values and rewriting the equation. So if we write N maximum in place of N max, we will write the 1 by cos phi, and for R if we write V square by G N square minus 1. So we can write that N max minus Bg by 2V square under root N square max minus 1 minus whole under root 2W by SW rho V square CL maximum N maximum cube is equal to 0. N maximum can also be written as NPLL W maximum by W. So in place of N max, we will write NPLL W max by W. So we get here that V square minus under root 2n PLL W maximum by SW by rho CL maximum V minus BG by 2 under root 1 minus W by NPLL W maximum whole square is equal to 0. Now we have this expression. So we can find out then we can get the root of one of these will be the velocity. So we have to solve this equation. It is a quadratic equation, and b square minus 4ac by 2a. By that we can solve, and then we will get that VR minimum velocity for the minimum radius, that is VR minimum is equal to under root NPLL W maximum divided by SW divided by 2 rho CL maximum plus whole under root NPLL W max by SW 2 rho CL max plus BG by 2 under root 1 minus W by NPLL W max whole square. This is the velocity that allows minimum turning radius without stall. So this is the velocity, minimum velocity where stall will not happen and no structure damage will take place. This is the tight maneuver. This is called the tight maneuver, means a minimum radius it should fly. So if I take it here, so this is the radius, so it is turning like this. So minimum radius, in the minimum radius, this is the velocity which we have to fly the aircraft so that stall will not happen. So spanwise velocity is not much like a glider. If it exceeds the max CL, then induces a spiral which is very dangerous. If we put the velocity VRNN in radius equation, we get the minimum radius. So from here we have got the minimum radius R. In that, if we put this velocity, we can get the R minimum. So like this we can find out the minimum radius of the aircraft. In the next lecture we will see the takeoff and the landing performance, introduction, common characteristics, takeoff principles, takeoff phases and ground roll distance, derivation of ground roll distance, forces during takeoff, average acceleration method. These are the references: Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's first edition, SL by Aircraft Performance Theory and Practice, AIA Education Series, AIAA 2. Any questions, any queries, you are welcome to ask. My email ID is yddwivedhi@gmail.com. Please do like and subscribe this channel. Any queries you can put into the comment box or you can send to my mail as I have mentioned here. Till then, goodbye. Thank you. See you soon in my next lecture. Till then, goodbye.
Like, share and subscribe. Hit the bell icon for more updates.